I am Dr. Vijaya Gowri, working as Associate Professor in Department of Civil Engineering in B.V. Raju Institute of Technology, Narsapur. Today's session is on train resistance and tractive power. This is one of the topic of railways, airports and harbour engineering. Overview of this session consists of the train resistance, which is due to friction, due to wave action, due to wind, due to gradient, due to curvature, due to starting and acceleration. And also another topic we cover train tractive effort of a locomotive. This tractive effort is different for different engines. So we cover tractive effort for steam engines, diesel engine and electric engines. So first we are going to find what is train resistance. Various forces of resistance due to the movement of train on the track is known as train resistance. These resistance may be result of the movements of various parts of the locomotive as well as friction between them and irregularities of track profile and atmospheric resistance to the moving at a great speed. The tractive power of locomotive should be adequate against these resistance for safe and smooth movement of train at a required speeds. Next, this track resistance due to friction we are going to see first. So, train resistance due to friction is the friction offered by the friction between internal parts of the locomotives, wagons as well as between the metal surface of the rail and the wheel of the train moving at constant speed. This resistance is independent of the speed and further broken into different parts. In that, first one is the general friction. This is depending on type of the bearing and lubricant used, and also the temperature of the bearing and the condition of the bearing is also depends. In the case of roll bearings, it varies from 0.5 to 1 kg per ton. So next one is the internal resistance. This resistance is consequential to the movement of various parts of the locomotive and wagons. Rolling resistance is the rail wheel interaction on the account of movement of steel wheels on a steel rail. The total frictional resistance is given by empirical formula. So R1 is equal to 0.0016 W. W is the weight of the train. Here, this type of resistance is not depending on the velocity or speed of the train. It is independent of the speed of the train. R1 is the frictional resistance depending on the speed. W is the weight of the train in tons. So, the second one is the train resistance due to the wave action. So, the train moves with a speed. Certain resistance is also developed because of the wave action. This is mainly because of the irregularities in the railway track, that is longitudinal unevenness and differences in cross levels offer the resistance to the moving train. Such resistance are different for the different speeds. So, it is depending on the speed of the train. There is no methods to calculate this type of resistance, but with experience they developed some formulas. So, RT is the train resistance due to the wave action, which is equal to 0.00008 W into V, where W is the weight of train in tons and V is the speed of the train kilometer per hour. So, here R2 is the train resistance due to the wave action directly depending on W weight of train and velocity of train. So next is train resistance due to the wind. So when a vehicle moves with a speed, a certain resistance is developed on the vehicle. The vehicle has to move forward against the wind. So this wind resistance consisting of side resistance, head resistance and tail resistance. But exact magnitude is depending on the size and shape of the vehicle and its speed and velocity of the wind and direction of the wind. So wind resistance is depending on the exposed area of the vehicle and the direction of the wind. The way the train is moving, this is the plan of the train. The wind, the direction is very important. In which direction it is acting on the vehicle and exposed area of that particular wind. So here this is the diagram. You can see resistance due to the wind. This is the direction of the train movement and the wind is acting in this particular direction, which is theta angle with the horizontal. So the velocity of the wind is definitely affect the movement of the vehicle. It is causing some resistance on the movement of the vehicle and it is divided into the two components, V cos theta, which is acting headwind to the train, and V is V sin theta causing side resistance on the movement of train. So the maximum angle which exerts maximum resistance on the train movement is 60 degrees. So there are the formulas are also developed for the train resistance. R3 is equal to 0.000017 AV square. So here R3 is the train resistance due to the wind and A is the exposed area of the vehicle in meter square. V is the velocity of the wind in kilometer per hour. Here R3 is directly depending on the exposed area and the square of the velocity of the train. There are some more important factors that affect wind resistance than the exposed area. It is also depending on W weight of the vehicle and speed of the train. The earlier V is the velocity of the wind in kilometer per hour. Here in this case we consider the velocity of a train and weight of the vehicle. So in fact wind resistance is depending on square of the velocity of the wind. So the following formula is based on the weight and velocity of train. So R3 is expressed in tons and V is the velocity of train in kilometer per hour. W is the weight of the train in tons. So next, the train resistance due to the gradient. Definitely because of the gradient, when the train is moving in upward direction, so some resistance is also offered in opposite to the direction of the movement of the vehicle when it is ascending. So W is the weight of the train and R weight of the wind and OA is the rising gradient. On the following forces, here we can observe that W is the weight of the wind and N is the force which is acting normal to the surface OA and R is the resistance which is acting opposite to that. So here these three forces are meeting at Q. So here we can observe two triangles, that is triangle OAB and QCD. They are two similar triangles. From this diagram, we can write this R is equal, we can write this sin theta is equal to R divided by W. So R is equal to resistance due to the gradient, that is equal to W into sin theta. Okay, because of these two similar triangles, we can write it as R by W is equal to AB by OA. We can write resistance is equal to W into AB by OA. So, since the gradients are very small, we can write it as R is equal to W into AB by OB. AB by OB is equal to tan theta. So, tan theta is nothing but the slope. So, we can write it as equation R is equal to W into percentage of slope divided by 100. So, it is resistance due to the gradient is directly proportional to the slope of the gradient, slope of that particular track. So, this means that if the weight of the train is 50 tons and the slope is 1 in 50, that is 2%, we can directly substitute and find out the R4, that is resistance due to the gradient is 1 ton. It may be noted that when a train ascends a slope, the extra effort is required to pull the train to overcome the resistance by the gradient. And if in the case of the descending the train on the track, this resistance due to the gradient will help the movement of the train. Next is resistance, train resistance due to the curvature. So, when a vehicle moving on the curved track, definitely it subjected to some resistance due to the curvature. This is many reasons for gaining the train resistance due to the curvature. One of the reason, first reason is because of the rigidness of the wheelbase. This, when the vehicle is moving on the track in the curvature, negotiating on the curvature, these wheelbases, the axles are not adopting that particular direction. It is moving tangentially. You can see here tangentially to the curve and they are moving. Because of this, the inner side of outer wheel, this is the inner side of the outer rail, and that side of the outer side of leading axle, outer wheel of leading axle will cause rubbing each other and causing the resistance. So, this is the wheelbase. So, the wheel is like this. Okay, so this is the outer wheel, outer rail, inner surface of the outer rail and outer surface of the leading rail. This is the leading axle will cause the train resistance to the curvature because of the rubbing each other. Some curve resistance is also can sometimes causing the longitudinal slip. This causes the forward movement of the wheel on the curved back. Trailing axle, outer wheel of the trailing axle will tend to derail because of this. The curve resistance is also caused when transverse slip occur and increases the friction between the wheel flanges and rails. One of the cause for curve resistance, poor track maintenance because of bad alignment, worn out rails, improper levels also increases the resistance. Super elevation, inadequate super elevation is also causing the problem for movement of the train. This will cause curve resistance. So, super elevation generally provided near the curve to counteract the centrifugal force. So, centrifugal force pull the vehicle to come out from the vehicle track. It will not negotiate to adopt the curve. It will want to come straight forward. So, we provide super elevation to counteract the centrifugal force. Inadequate super elevation will cause some pressure, more pressure on the outer wheels, more for the outer wheels of the axles. So, similarly, more super elevation or excess super elevation will cause the pressure, more pressure or tractive resistance due to the curve will be more, and curve due to the pressure will be more in the inner wheels. So, the value of curve resistance determine the following. Curve resistance is equal to C into F into G divided by R. F is the force of sliding friction, G is the gauge of track, R is the mean radius of the curve. C is the constant. So, the curve resistance is increases with the increasing the force of sliding friction and the gauge, and it is decreases with the increasing the radius of the curvature. So, this directly depending on the gauge. So, the curve resistance is given for broad gauge, meter gauge and narrow gauge. For broad gauge, that is 0.0004 WD. For meter gauge, 0.0003 WD. And for narrow gauge, 0.0002 WD. This directly depending on the weight of the train in tons and also depending on degree of curvature. For example, 4-degree curve on BG line, the curve resistance for the train weighing 250 tons would be 0.0004 into 250 into 4. We will get 0.4 tons. That means the curve resistance will be 0.4 tons. Next is the last one, the train resistance due to the starting and accelerating. So, the train faces these resistance when it is starting and accelerating. It will cause some pressure and for movement of the vehicle on the rails. It will cause some pressure and some resistance to the movement of the vehicle. So, resistance on the starting R6 is equal to 0.15 W1 plus 0.005 W2. W1 is the weight of locomotive and W2 is the weight of wagons. And here resistance to acceleration R7 is 0.028 AW. Here weight is equal to W1 plus W2. So, A is the acceleration and W is the weight of the vehicle in tons. So, R7 is resistance due to the acceleration directly proportional to the acceleration and weight of vehicle. So here the table resembles summary of nature of resistance and value of resistance and some remarks of that different types of resistance. So resistance due to the friction R1 is equal to 0.0016 W. Resistance is independent of the speed. Resistance due to the wave action or track irregularities and speed 0.00008 WV. It is depending on the speed of the vehicle. Resistance due to the wind or atmospheric resistance R3 0.0000006 WV square. This is resistance dependent on square of the speed. The resistance due to the gradient R4 W into percentage slope. Resistance is depending on the slope. Curve resistance for BG R5 0.0004 WD. Resistance dependent on degree of curve. So resistance due to starting R6 is equal to 0.15 W1 plus 0.005 W2. The resistance depending on the weight of the train and locomotive. So resistance due to the acceleration 0.028 AW. It is directly proportional to acceleration and W. So it is dependent on acceleration and weight of the train. So the train tractive effort of locomotive. So tractive effort, what is tractive effort? So the tractive effort is the force that the locomotive can generate hauling the load at a maximum permissible speed. So there are the various tractive effort curves available for different locomotives for different speeds, which enable the computation of the value of tractive effort. So that's why different trains requires some tractive power differently. So we are going to see for the three types of locomotives: steam locomotive, diesel locomotive and electric locomotive. Tractive effort generally equal to little greater than the hauling capacity. It should be little greater than, not greater than, little greater than hauling capacity. If it is greater than, much greater than, then what is required to haul and train, the wheels of the locomotive may get slip. So tractive effort for steam locomotive. So the tractive effort of steam locomotive can be calculated by equating the power generated by the steam engine and the work done by the wheels, driving wheels. Assume that P is the difference in steam pressure between the two sides of the cylinder. A is the area of the piston of the engine and D is the diameter of the piston of the engine, and L is the length of the stroke of the engine, and D is the diameter of the wheel of the locomotive, and T is the tractive effort required for the locomotive to overcome the resistances. So work done, we are going to first calculate the power generated by the steam engine, that is equal to 2 into P, the difference in steam pressure in both sides of the cylinder. A is the area of the piston of the engine, L is the length of the stroke. So we have to calculate by using the 2P into A into 2L for finding the amount of steam power. So this is the pi P D square L is the steam power, and work done by one revolution of the driving wheel of the locomotive, that is equal to tractive effort into circumference of wheel. So from this we can calculate TE into pi D. So equating the steam power is equal to work done by the wheel. So this equating this one, then TE is equal to P into D square L divided by D. So tractive effort increases with increase in the P D square of diameter of the piston and length of the piston. So tractive effort is decreases with increasing the diameter of the wheel. Next is the tractive effort for diesel locomotive. The tractive effort of diesel locomotive is assessed by the empirical formula TE is equal to 308 into RHP divided by V. So, TE is the tractive effort of the diesel locomotive, RHP is the rated horsepower of the engine and V is the velocity in kilometer per hour. Electric locomotive. So, the tractive effort of electric locomotive varies inversely with the power of speed. Here empirical formula is also given for the calculation of the tractive power for different electric engine. There are the DC electric engine, AC electric engine. For a DC electric engine, TE is equal to A divided by VQ. And for AC electric locomotive, TE is equal to A divided by V to the power of 5. So, the speed increases, the tractive effect is going to be decreased. A is the constant here. So, this is about today's session. We have seen the tractive effort and also tractive resistance, train resistance. The train resistance due to the friction, wind, gradient and curvature and starting and accelerating and wave action and train resistance, train effort for the steam engine, diesel engine and electric engine. This is the thing we covered today's session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.